Welcome back to Realize Live. This is Mark Sampson. I'm a systems engineering evangelist here at Siemens Industry Software. So I'm here to talk to you about an integrated model-based systems engineering journey that either you're on or will be undertaking to deal with this growing product complexity. We've chosen the integrated MBSE label because that's the only way we're going to be able to get the value of the cross-domain perspectives that systems engineering offers. And it needs to be part of the PLM or product lifecycle in order to drive that perspective across the entire product development process. So let's start with some motivation. As a teenager, I apparently wasn't moving fast enough for my grandmother, who was a noted philosopher in my family, and she pointed out to me, she said, "You know, Mark, there's a difference between jogging and being chased by the bear." She's right. So let's talk about some of the bears that are chasing your organization. So back in 2018, for example, the automotive industry had some 443 of these recall problems that affected some 47 million vehicles. The National Highway Traffic Safety Administration, which manages this in the United States, says that the each recall costs about $100 per recall per vehicle. That's $4.7 billion as direct costs that was spent on these problems back in 2018. Now, 2019 was about the same with 42 million recalls. And the problem, of course, continued into 2020 with some 54 million of those recalls, which accounted for 5.4 billion in direct costs. And many of these recalls have to do with the integrating of requirements and other interactions across the product lifecycle. So we need an enterprise solution because many of the product compliance escapes happen at the cross-domain level instead of any particular domain. This means that system architecture requirements need to be related across the product domains in order to make a difference and to catch these things early. So of course, it's just not happening in just automotive, it's happening in nearly all industries. For example, in aerospace. Now, Norm Augustine, who is the legendary Lockheed Martin CEO, he was right. If you look at his law number 16, he talked about we're going to reach the point where we can no longer afford to make airplanes. So the aero business is actually reaching the limits of affordability due to complexity. As this graph from the Aerospace Vehicle Systems Institute describes, MBSE is a consortium of aero companies looking to achieve quality at a more affordable price. Now, MBSE has a number of projects underway, including System Architecture Virtual Integration, or SAVI, which has been researching and monitoring many different measurements of system complexity. One of those that it's measuring is source lines of code. So you can see, if you're looking at this graph, that we've reached the level of unaffordability, mostly driven by integrated late in the product development life cycles. Now, they recently added the military aircraft as well, and you can see here from this quote. Now, Savvy states that we need to change the way that we do business from the spec, build, and then integrate with suppliers, as this is no longer affordable. We need to start integrated and stay integrated, or as they say, integrate, then build. So this is a symptom of organizations, disciplines, and complex system interactions that are all attempting to communicate in disconnected ways. Now today, without a digital thread, organizations and discipline boundaries create barriers to communications, resulting in communication engineering problems at those boundaries. So for example, a requirement change on one side of the barrier isn't communicated to the other side. The later those lost communications are discovered, the more expensive it gets. But you already know this, and in fact, you actually set aside half your program schedules and resources to be able to deal with these integration problems. So integrating system models and their requirements with the product lifecycle allows product architecture and requirements to drive downstream development. With the requirements and the architecture elements flowing across the entire organization, what it does is it allows us to improve communications that eliminates these barriers at the boundaries of disciplines and organizations, so you can eliminate these kinds of problems that are happening and are typically not discovered until late in the product development process. So looking at this process with a standard V, and walking around this happens to be a 4754 aero type systems development process, you can see all the silos and the disconnected artifacts they produce. What this does, of course, is it disperses the voice of the customer. There's no single source of truth. The lessons learned might be captured, but they're not passed on. And you're not able to see reuse opportunities. So you don't get all the benefit of the traceability or change impact understanding that you need to pull this off. So the result is that you end up discovering these problems late in the product development process. during system integration. Now, you already know this, of course, and in fact, you plan to have as much as half your program schedules and resources to deal with it. That delays your time to market, and in the case of your suppliers, the time to revenue. So contrast that with this integrated MBSE vision that INCOSE, that's the International Council on Systems Engineering, uses to communicate the value of this MBSE solution and what it enables through continuous communication. So, for example, if we have this integrated MBSE solution, we should be able to ask questions of our vehicle. For example, maybe this is an autonomous vehicle, and maybe we received a regulatory change about emergency stopping distance. Now, in organizations, when you receive one of these changes, you would typically launch some kind of trade study, gather up people and time, and go try to find out where this part of this change goes. But because we got this integrated MBSE solution, we should be able to get some near real-time feedback from our vehicle that these areas of the vehicle might be changed. So let's look at this. We step in, and here we can see that there's two requirements that we're looking at, one on turn radius, one on braking distance. And let's say, for example, if we change this requirement from 110 feet to 90 feet, we should be able to see in a near real-time way these areas of the vehicle are potentially impacted as a result of this change. So from there, we can dive into it. For example, go into the braking system. And here we see 7 different models that are reporting in their perspective on the problem. At the 12 o'clock position, we see hydraulic flow is no longer compliant with the requirements. Okay. I think we probably would have expected a thermal model issue at the 3 o'clock position, but as we go around here, we see other things. We seem to be okay. Hydraulic pressure, but for some reason we've thrown a fault in our cruise control. Our mean time between failure calculators tell us we've got an issue, and for some reason we've gone to 18 amps on our electrical circuit. So we drill into that. We see we've gone to the fuse box, and we see we've blown a fuse. We can follow that to the schematics, and from there to the harnesses. And for the first time, we realize that we have a relationship we never knew existed before. In this case, when that sensor failed, it caused this cascading effect. So now we have a new failure mode that we have to worry about. Let's get that captured. And while we're here, we might as well look at the MATLAB model, which was used to generate the code in the cruise control, get that problem corrected. And while we're here, we might as well go ahead and look at the insurance rates, the actuarial tables, because we should be able to get a better deal on our insurance as a result of this. Now that view is only available because we're looking at the cross-domain perspective. In other words, we reached a high enough altitude that we can look down and see those perspectives. No one tool would have highlighted that issue that would have shown up at 3,000 hours in a customer's driveway. Now to achieve that vision, you'll need to follow a standard process. So that process begins at the far left of here, at the system of system level, where we want to see all the things that are interacting with us in the outside world. Here's where we understand the interactions with other kinds of systems. So for example, an airplane has to deal with air traffic control systems, maintenance systems, airports, the list goes on. Once we get that documented and understood, then we can define the scope and the constraints and the things that we have to constrain our design against. Out of that process comes a set of use cases and demands that would constrain our overall development process or design. We sub-select to a subset of requirements, and then we start looking at concepts or ways of doing this. The more what-ifs we can look at, the better off we are. So from there, when we choose a concept we want to pursue, then of course we go to derive requirements and start looking at the system design. And from there we go into the downstream development environments, mechanical, electrical, software, and so forth. And eventually that's where we get into the design aspects of it and into our product data management or bill of materials world. And from there down to the manufacturing and into as built, as maintained, and so forth. Of course, Siemens solutions support this process in an integrated way. Here you see the various domain-specific solutions that how they fit into this development process. The front-end product development or product definition part of this product definition process or development process is where the product architecture is defined and where the greatest leverage is at for avoiding these kinds of downstream development problems that we discover. This makes the product architecture one of the most important aspects of this product development process because it essentially acts as a blueprint that can be used throughout the entire product development process to make sure all the various disciplines and everybody involved is working from the same sheet of music. Now the product architecture and product definition process is supported by the system modeling workbench, team center requirements, sim center, team center generally. And what we're going to do is we're going to focus in on the value of system modeling workbench and requirements in this product development process. So now compare that with what you're doing today in your organization, compare that with a vision of what you've seen. what we would call insanity going on inside your organizations. You all know the quote from Einstein about doing the same thing over and over again, expecting a different outcome, which is exactly what we find out is going many organizations because they don't have the value of this integrated digital thread or systems engineering thread that runs through all these various domains. So here's a simple example of a warranty issue about a driver getting wet. I have the opportunity in my travels to talk with many different engineers in many different industries. I was talking to one engineer, and she was talking about how during a training exercise, or I'm sorry, as part of her training process, they put her into various parts of the organization. And they handed her this problem, water on the knee. So she did the investigation. She found the car. She opened it up, and she realized what was happening here was the fact that water gets inside these doors. And in this particular case, let me see if I can get my marker out here so you can see it. She found out the water was splashing around and was going down into the speaker. When it reached the speaker down here, what it was doing was if you had your full bass turned on, it was splashing the water through the speaker into the passengers. Now, as she looked at the harness there, she recognized it had a number of revs on this harness, and she found out that in the prior version of the harness, it had a loop of wire inside that harness. And of course, what that loop was doing was it was performing the function of keeping the passengers dry. But because nobody knew it was there and was performing that function, what was happening is, since we're talking about a lot of cars here, that they looked at that as being wasted 4 inches of wire, and therefore they eliminated it. It went back and forth like this about every 6 months, she said. So that got us thinking about, well, how many problems are just like that, and just how insane is our behavior in other kinds of areas. So we've done a lot of gathering of information and metrics, and we found out, for example, in automotive, it's about 3 years. High tech, that resurface metric, how long does a problem with solve take to come back, is about 6 months. In aero, of course, because they're longer life cycles, it goes longer time. But as we looked at that, as you look at these problems that are at the cross-domain level, multi-domain level, these are a result of siloed or disconnected design decisions, as you see here. We found that these problems seem to follow function. In other words, just as architects are taught about form following function, well, problems follow functions as well. Everyone needs to be involved in this decision-making process, because sometimes somebody has a different perspective, including things like purchasing, for example. They're the result of disconnected requirements, because the requirements aren't at the same place, so you're making a decision. You end up making a decision without the benefit of understanding what the requirements are. The result of oftentimes of uncommunicated change. Something changed somewhere, it wasn't communicated to you. But they happen at the domain boundaries, and they migrate with people, either overtly or covertly. In other words, if that person that saw this problem before wasn't there for whatever reason, maybe they moved on, that means the problem has an opportunity to come back. And of course, it's happened as a result of this disconnected product architecture. We don't have the benefit of a set of blueprints. So we got thinking about this, and these are all the things that systems engineering is supposed to be doing. They're supposed to be worried about functions, they're supposed to be worried about requirements, change impact, interface management, and so forth and so on. So what we did is we got thinking about how it is we might measure this kind of sanity that's going on in an organization, or insanity. And so if you look here at the far left side here in column A, we see here a list of things that systems engineers are supposed to be doing. This is as described in like ISO standard 15288 or IEEE 1220 or EIA 632. There's a number of these system standards out there. They all describe this process that is supposed to be doing things like architecture and targets and logical modeling and so forth and so on. So as we got talking about that, as we were thinking about that, we got thinking, well, they could be doing this job in any number of ways. They could be doing it in a disconnected way, where with documents, or they could be doing it in a continuous way or a connected way. So remember, what we're after is having to start integrated and stay integrated, or doing it continuously rather than finding out late in the development process that we've got a problem. So for example, if I take one example here, like for example, requirements management. You could be managing requirements in uncontrolled spreadsheets. You could also be managing requirements in document or SharePoint. You could be managing requirements in standalone type requirement environments. There's lots of them out there. But as you move from left to right, from disconnected to connected, what you're after doing is getting these requirements so they show up at the right place at the right time in such a way that they have the opportunity to influence requirement or design. So As you move to the right here, you'd like those requirements to show up places, like, for example, inside of the MATLAB model, inside a CAD model, and so forth. The best of all worlds would be over here on the far right side here, where we're actually managing individual requirements, that these little requirements by themselves have their own life cycles. They're part of the overall product configuration. And because they're part of PLM, that means that I can get the cross-domain traceability I need. For example, a requirement change, I can see the functions, the parts, the manufacturing processes. I can see the program schedules, the tasks, the test cases, so forth and so on, that are all impacted as a result of this change. Let's pull another example here for you. For example, in the area of interface management. Interfaces are very important because this is where all the bad things in a product's life happen, is at the interfaces. And in fact, that's essentially what system engineering is all about, is managing those interfaces in such a way that the bad things don't happen. So if I ask you, for example, how you manage interfaces, you can tell me, I manage my interfaces in a document. That's an interface control document, and some people will say that's the most important document in a program. And as you move to the right there, you begin to move to managing individual interfaces, for example, to managing libraries of interfaces, to managing reusable chunks of those interfaces. The best of all worlds would be that we are managing not interfaces at all, but we're managing the fact that these functions that we designed or wanted our product to accomplish are being accomplished in various places. So when I allocate a function to something, I essentially am birthing an interface, and the end result is that I can see where it goes. So for example, if it's integrated with the product lifecycle, so it's showing up everywhere, that means I could ask a wire, for example, what are you doing here? Or a hydraulic line, what are you doing here? And it could tell me what functions it's performing. That's a powerful idea. So what we did is we've taken this idea of assessing where we are in our design sanity, and then what we've done is we've taken it, we've gone off and visited a variety of industries and a variety of places, and we've developed a curve, if you will. This is a standard curve that you're looking at here of where everybody is regarding the maturity of MBSE in their organizations. You can see here that we're all challenged and we're all doing insane behavior. What this says here is that we're predisposed to insane product development processes where we continually rediscover problems that have been solved in the past. And we don't discover these problems until late in the development process, and it ends up consuming half our program schedules. Now, by the way, I should point out to you, this is an optimistic model. We ask responders to think about the best practice they've ever seen in their organizations, so it represents as good as it gets in those organizations. And you can now imagine what the problem progress look like. Now we've taken these best cases, for example, and we've actually extracted, here's the best case we've ever seen in Aero, here's the best case we've ever seen in Auto. And now we can predict about where you are. Based on the average, you're probably around here. That's important to know where you are, because after all, this is the first step in getting better, right, is to understand where you are. And we're talking about here is a journey to the right, with our goal here of moving you to the right in your maturity so you can shift your product development to the left. Essentially what we're after doing is this is an opportunity to slash your integration cycles in half. So, one question you might have then is, well, where do I start, right? There's a great quote here from Arthur Ashe: start where you are, use what you have, do what you can. We spend enough time at these organizations that we think that we can give you some advice on where you should start. We think if you're at level 1 kind of an organization, you want to start with getting your requirements under control rather than documents. Get them inside the product lifecycle so they can have the opportunity to influence your product development process. This will give you confidence in the requirements and enable a requirement-driven process. Okay? Then, as you move to the right, you might start here if you're more advanced. What we're talking about is beginning to moving up to the product architecture and getting the requirements along with the requirements into the PLM, because the next logical question is, behind the requirements, how do you know these are the right requirements to be managing? So you'll start looking at the architectural aspects of that. Now what this will begin to do is it will enable your project or your chunk of project reuse and change impact understanding now versus later, and also help you begin to solve this cross-product communication problem you currently have. and it's consuming so much of your program. From there, of course, what you want to do is start to move up to the to level 3, which of course moves you into up the integrated architecture, and to enable the supplier collaboration. Now, you guys know that you're just not you doing this product development process. You need to get your suppliers involved in this. And so we're after taking our architecture that we now have inside our PLM system, along with the requirements, and collaborating with our suppliers in such a way that we can get them involved in this process in a continuous validation and verification process. Now, this has access, of course, to all the PLM services like configuration and change and variation and so forth. So you have the benefit of that, as well as being able to share this with your suppliers. And from there, of course, we go to even higher levels where we get to this systems engineering digital twin by merging the virtual and the real so that you can actually achieve what we call this continuous integration. So this, of course, can drive the downstream discipline development in an integrated way. And that, of course, supports the focus processes. What I mean by a focus process is rather than, for example, you now have the traceability that's going to tell you what things are potentially impacted across the life cycle. And rather than testing everything since you don't know where it goes, you now begin a focused testing approach where you only test those things which are affected by this change. That's going to allow you to get validation and verification or test off the critical path and allow you to start seeing with the confidence of where a change goes and how its effect. So we're talking about moving you in a gradual way on a journey from level 1 up to 3 and up all the way to 4. So you have this ability to move from this disconnected to integrated product development process. It's all going to be enabled by this integrated product architecture and requirements showing up at the right place at the right time. So does this work, or is it worth the trip? Does switching to this model-based approach where from continuous integration that enables multiple domains to collaborate through this architectural thread, is it worth it? Here's proof from Boeing when they did a presentation back in an earlier user group meeting on 787. So Boeing, in their presentation, you can see here, this is the subsystems that were being managed on the 787. What they did is they mapped the various subsystems to each other and established the dependencies. You see, I've just drawn a few of them here for you. There were millions of these interactions that are going on inside a 787. So what they did is they once they got those relationships in place, then they established a publish and subscribe system where a change in one spot would ripple through all the dependencies to the other spots, other subsystems, so everyone everywhere was understanding what was going on. And it demanded an answer about whether they were impacted by it or not and how to justify why they weren't or why they were. It also enabled communication the other direction where the subsystems could request changes to the super systems. So what they did is during their presentation is they showed us this graph. This graph shows 3 different aircraft programs. This one here they said was 777. Let me see if I get the marker here, sorry. Here's 777. They said that on first flight 777 found 16,000 plus integration problems. They said that accounted for 1.5 years of schedule. The other one, I'm not sure what that is. We could probably make a trajectory to guess, but the other one I want to point out to you here is the zeros. They're along here. Because they had this system in place where everyone is continuously on the same page, everyone working from current data, and being informed when changes happen across other systems on them, they were fully integrated continuously. So the end result is that they had 0 squawks or 0 integration problems on first flight. That's a powerful statement. The ability to actually deliver a product on time, on schedule, because you know everybody's continuously integrated is a much different problem to a very powerful idea. So here's my contact information, and we'd like to make you a special offer. If you'd like to see where your organization's MBSE maturity is compared to others in the industry, give us 30 minutes of your time. With the people in your organization, you can actually know the answers to how your product development process works. In exchange for your honest answers, we'll give you an assessment of where you are, along with how you compare with your industry competitors or other industry areas. Of course, this will all be anonymous, but it will give you the opportunity to see, and it will actually enable a conversation about where you are and where you can improve. So with that, maybe some additional parting motivation might help you. My grandmother also used to say, if you motivate me without enabling me, then you frustrate me. She was a smart lady. Hopefully you can feel the motivation, and hopefully we've given you some places to go. We're hoping you'll let us help you on this integrated MBSE journey, because currently it's consuming half your program schedules. So with that, thank you very much, and let me know if you have any questions.